All right. Hello. I'm just going to check the stream is working okay, and then we can get started. All right, so does this seem fine? Sounds all right to me. Cool. So, just going to give people a minute or two to get in here, and then we can see. Maybe not in a full minute. Let's see. I can already go ahead and open up the relevant pieces of the WebAssembly spec, because we're certainly going to need that in a bit. Except this time we're not going to be so busy dealing with the binary format, because that encoder has been finished, at least for the parts that we need or are going to need in the foreseeable future. And I think we can probably just work off of the structure part of the spec for now. All right. So, what are we going to do today? Well, I did a bit of work off stream, and I have finished the encoder for WebAssembly. So if I go over here and we check out the write module function in our encode, you can see that it encodes all of the sections. And I have written the bits of, and I mean, it's totally possible that we'll find bugs in here today, but for now, this should be good enough. I have also gone ahead and extracted the dynamic buffer we've been using to write out our bytes into a library. So I'm hoping that this could potentially also be useful for someone else. So it looks like people have noticed I have opened a PR against the new PureScript registry. But oh wait, it's down here. But I have not gotten any feedback yet. But I mean, it's the weekend, so maybe we'll get a response here. But for now, because Spago is awesome, I can just go and add the dependency on the package down here, and then go into the packages.dal file and actually just add that dynamic buffer dependency down here. It's a very light dependency in the sense that it doesn't actually depend on anything that you wouldn't have in a regular project anyway. So this is just type definitions, effect, and refs are basically bread and butter. And I've FFI'd a few other things just to make it so that, because this thing is basically tied to the Node Untitled API anyway, so I made it that this had as few dependencies as possible, so that would be nice and lightweight. So yeah, and this is the encoder. We might write this in a bit of a nicer fashion at some point, but actually the explicit passing of the buffer doesn't bother me as much as I thought it would. And I think putting an extra monad in here actually makes the thing more noisy, but we'll see about that in the future. For now, I'll just leave it as is. and I've tested this and it seems to work fine. So what we can do now is I can say, well, I have defined the empty module here, which is the empty WebAssembly module, which doesn't have any any contents really, and I can run that through our encoder, and when I run obj dump on it, which gives us -x means that it's showing us all of these section details. So, well, there's no sections in this module, and -d disassembles the code, and there's no code in here, so that's why all of this is empty. But this means that it's successfully writing out the WebAssembly binary format. And what I want to do today is actually create a module that represents a program in a higher level language, so, or like in a higher level expression syntax that we're going to write today. So my goal is that I want to be able to, by the end of the stream, input something like 3 + 4 × 5, and maybe I'll just maybe we'll not write a parser and just have this be abstract syntax for now, because I can't, like, this is not a stream that is about parsers, it's about WebAssembly and compiling to WebAssembly. But what I want to be able to do is I want to be able to insert something like this and then generate the corresponding piece of WebAssembly and have a WebAssembly module we can run that produces this number. All right. And I don't want to do this in the main file, so I have created a new module over here, which I've called compiler.pers, and it's a completely empty module, but we're going to have the test module here, which is going to be a WebAssembly module, and we're going to refer to the WebAssembly module stuff a whole bunch, so I'm just going to qualify that as S. And this test module right now is just the empty module, but it's going to be more interesting in a bit. And then we can delete this and say, well, yeah, test module, you're going to import that from compiler, like so. And then we no longer need the syntax in here, which that seems just right to me. All right, and please feel free to ask questions at any point in time. That's kind of why I'm doing this. So really what I'm doing here is preparing for a bunch of recordings I'd like to do at some point that show this in a nice compact manner. Right now I'm just figuring out what the nicest way of presenting this to someone is. All right, so let's talk about the WebAssembly execution model, or let's start out a little. Let's actually start in our world for now. So what we want to do is we want to say, let's say we want to compile the expression 3 + 4 to WebAssembly. Okay. And so now what we could do is we could say, okay, 3 + 4, we're going to add together the numbers 3 and 4. So let's look at the WebAssembly instruction for add, which is I32 add. But you can see there is no 2 arguments over here or something. This is just a naked instruction, right? There's no additional arguments to it. And the reason this is because WebAssembly is a stack machine. Okay, so the execution model is that of a stack machine. And I'm going to hope that this is going to work out. I haven't used this program in a while, but I'd like to draw a bit and explain what that means. So WebAssembly is a stack module, is a stack machine. So what we have is a stack. Okay, and if you're not familiar with the term, a stack is a data structure which has a top, and you can add elements at the top, and you can get the elements that are at the top. Okay, so our stack is actually going to grow downwards. So so right now this is the empty stack, but I could say push the value 4 onto it, and then the value 5. And now when I pop a value off of the stack, I'd get the 5 back, and it would be removed from here. Okay, so this is our stack, and it grows downwards. I'm gonna signal that by putting the arrow okay, that's a terrible arrow, by putting an arrow in here, like so. Okay, and then the second thing we have, and there's actually a third, but we're not going to bother with that for now, is the set of instructions we're processing. So in WebAssembly, we have a stream of instructions, or like a linear sequence of instructions that we are executing. Okay, and these instructions correspond to the instructions the spec defines over here. Okay, and these are all the instructions. We have them, maybe I could show them over here. So if we go in here and we find the instructions, we can maybe look at, well, there's about a whole bunch of them, right? But maybe we can get an, maybe we could, well, this section is enough for now, because I think that's all the numeric instructions we need. Okay, so let's get back here. So the stack is empty. And now what we want to do is we want to add the numbers 4 and 3. So we can't just say I32 add, because what add expects is 2 numbers to be on the stack. Okay, and so what we need to do first is we need to push the 2 values that we want to add onto the stack. So what we need to do is we need to say I32 const. So this is, so we're saying we want to push a constant onto the stack. And I think we said we wanted to add the numbers 3 and 4. So we're going to say I32 const 3. Then we're going to say I32 const 4. And then we're going to call I32.add. So what's going to happen? And again, the instructions are also executed downwards. So this is where we are right now. Okay, and what's going to happen is when the interpreter sees this instruction, what's going to do is going to push the number 3 onto the stack and move on to the next instruction. Okay, so now we're at this instruction over here, and this is the same thing. It pushes the number 4 onto the stack, and then it moves on to the next instruction. So what happens when it sees an add instruction? Well, it pops 2 values off of the stack, adds them up, and then it puts the result value back onto the stack. So this pops 3 and 4, and it adds the value 7 to the stack. Okay, and so let's see if we can go into PureScript and produce a module that produces this sequence of instructions. If there's any questions at any point in time, please just let me know. All right, so let's go into our compiler module. Here we are. So this is the empty module, and we're going to use PureScript's record syntax here to say, well, we want to edit the instructions. So if you look at empty modules here, you can see that the instructions, oh, it's not insters, it's the funcs, I believe, that we need to edit. So we need to say funcs. So right now that was an empty array, but we are going to add a function here. So what is a WebAssembly function in this format? Insert or follow as primes and views. Oh no. How do I moderate this? Is there a thing? I don't have. How do we remove the spammers? Sorry for the. Hey Yugi, hi Victor. Yeah, I mean, if it's just the one message, I'm not gonna mind. But if I get another spam of it, I don't know how to ban it right now. But if I see another one of those messages, I'll figure out how to moderate this. Okay, so what is funcs? Funcs is an array of functions, and a func is a record that is defined like so. So it has a type, which is a type index. It has an array of locals and a body, which is an expression. And if we check out what the body is, we'll find that that's an array of instructions. Okay. So what is a function? A function is a record with a type. Yeah, but I'm using the Streamlabs. So Victor is saying, yeah, you can right click his name. You should have the options in there, I think. So I'm using the Streamlab client on my machine right now to see the chat, and it does not give me these options. But yeah, this next time it happens, I'm going to go on Twitch and do it. Yeah, so thanks for the tip. Okay, so the type here is supposed to be a type index. That already tells us that we're missing something, right? Here, we need a type here. Then locals, so we're not using any locals yet. That's for local variables. We don't have those, so I'm just going to leave this empty. And then the expression, was it called body, I believe? Let me just check real quick. So func is defined as, yes, it's a body, which is an expression, I see. So so the body is an array of instructions, and these are the instructions we just saw, right? So we need a const 3, then we need a const 4, and then we need a i32 add, like so. And now it's saying, well, what's the type of this thing? And this is a type index. So I'm just going to say 0 here, but you'll see what happens in a second if I just try to compile this. So this is saying we're trying to index the signature 0, but there are 0 signatures. So what we need to do is we need to say, okay, we need to add a type to our WebAssembly module that corresponds to the type of this function. Okay, and so if we check out the types in WebAssembly, that's an array of func types, and a func type is an array of, well, an array of records of arguments and results, and both of these are arrays of L types. That's something nice about WebAssembly, is that it has multiple return values for a function. So we need a type here, and it's the index 0. So this is our, and the arguments here is our function does not take any arguments, and the result, well, after we're done, I think it results, we'll see, there is a single i32 on the stack, right? Because, well, this type system here represents what happens to be on the stack. And if we look at our example, when our function started, it didn't expect any arguments to be on the stack, and then it adds a single value onto the stack once it's done executing. So that's why this is the type signature here. Okay, and so now you can already see, though, that even though this is an invalid piece of WebAssembly, an invalid WebAssembly module, you can see that we've successfully added into the code section a single function which has the set of instructions that we expect that to be. So let's run this one again, and this time around we didn't get any errors. So we are now successfully creating a WebAssembly module. We have a type in here, and we have a function which matches the signature of this type, with this code, and this is the code. But as you can see up here, this is the exports that the JavaScript prints out for us. There is no export. We can't call this function yet. And so that's what we need to do next, is we need to add an export for this function. Okay, so let's check out what an export in WebAssembly looks like. So an export, it has a name and an export description. Okay, and an export description describes what we're exporting, and we are exporting a function here. So this is what we're going to go with. So an export has a name, and we're going to call this function, let's call it 7. And it's going to have a description, which is an export func. And export funcs expects the index of the function we're exporting, and the index here again is 0 because this is the first function that is defined in our module. Okay, so what this is saying is that the name 7 should appear in the output in the exports, and it should reference this function. Okay, and so if we compile this again, we'll now see that we have an export here which represents 7. And so what we can do now that we have an actual valid WebAssembly module with an export is we can use Wasm time to call the exported function here if we want. So we can go and say Wasm time run, and bytes.wasm is the file we've produced here, and we're going to tell it to invoke the function 7. And as you can see, it actually produces the value 7. So that's pretty exciting. Now, one more thing we can do here, and I haven't tried this yet, so we'll see if this works, is we can set a start function. So this is the function that this thing is supposed to execute when the WebAssembly module is instantiated. And that's maybe a function ID. And the default here is nothing. But we can say, well, just execute 0, right? Because that's the function we'd like it to execute here. And then I'm actually going to say, let's not export the function anymore. And so what we should be able to do now is if I compile again, we should be able to say, does it not like? It does not like invalid start function, non-zero parameter or return count. Okay, so a start function apparently is not supposed to return a value, which is kind of understandable. So let's for now, let's not mess with the start function. We can maybe get there when we deal with, when we use a few more advanced features of WebAssembly, but let's not do that for now. So what we have done here is we have created a WebAssembly module that has a function in it which adds the numbers 3 and 4. Now that's compiling by hand, and so the interesting bit now is going to be to try and take this expression and produce this expression down here. But let's actually make this expression a tiny bit more complicated so we can try and figure out, we can get a better understanding of how the stack machine works here really. So let's say we wanted to write down this expression in WebAssembly. Okay. And so let's say we have so what was this expression? This was 3 plus 4. So let's say we wanted to do 3 plus 4 times 5, and we want to bracket these up like so. That's a terrible line. Okay, so now we have, again, our insters and our stack. Okay, and what we're going to do is, so this is 3 plus 4 is 7 times 5, so this thing should be 35, right? But what we need to do is, if we look at this, we can't start with the multiplication really. What we want to do is we want to start with this addition and then do the multiplication here, okay? So what we're going to do is we're going to say, I'm going to leave out the I32 prefixes because everything here is ints. So we're going to say we're going to const 3, const 4, which is going to put 3 and 4 in the stack. We're going to add these together. Then we're going to, and so what is the stack after it has executed these instructions? Yeah, so we're done with this instruction, and so this is so really we're here. This is the next instruction we're executing, which we haven't written down yet. And this is the state of our stack. Okay, so what we need to do now is we need to add the 5. We put this on the stack. So now the stack looks like so, and then we say, well, multiply this too. And multiply does the same as add in the sense that it takes 2 values of the stack, multiplies them, and then it puts the result value back onto the stack. And so that's how we get 35. Okay, and so now you can I hope you can start to see how we use a stack machine to build more complex expressions. So let's just, for the heck of it, try and see if we get the expected 35 if we write down this expression in our compiler. So I'm gonna say, let's put these over here. I'm not entirely happy with the formatting, but I'm just gonna take whatever the editor gives me for now. And then, so we need to const the value 5 onto the stack, and then we need to do an I32 multiply. Okay. So let's try that. All right, we finished compiling, and let's invoke 7 again, but this time around 7 returns 35. So things work as we expect. Now, right now we're just writing down WebAssembly instructions by hand. Let's go ahead and get to the compiling bit. So when we compile something, we need a target. So the target language is WebAssembly, but the source language that we're compiling from is actually a different one. And so I'm just going to call this one. I'm just going to say there's a data type here, and let's actually call this one an expression. And so an expression, and now we're just going to describe the abstract syntax tree that represents expressions of this shape. So what can we have? Well, we can have a literal int. We can have a addition that adds together two expressions, or we can have a multiplication that multiplies two expressions. All right, and we can take our 35 and represent it in this data type. So 35 is an expression here now, and 35 is equal to, well, we're multiplying together, so that's the multiplication is on the outside. Then we have an addition, which adds together the literals 3 and 4, and we're multiplying the whole thing with the literal 5. Okay, and that is 35 over here, like so. Any questions about that? Well, just ask. I think this is reasonably clear. I hope if you've seen an AST before, you kind of understand what's going on here. Just indenting it a bit to make the tree shape more clear. You didn't call it exprovert. No, we don't do that kind of stuff around here. We do not do complicated things because we kind of want to focus on the things that this is about. So if we want to ever do a tutorial series on how to work with catamorphisms and that kind of nonsense, I'm more than happy to do one. But I have a feeling that it would make this series or this set of videos rather useless because people would get very lost in the details. And I really need to remember that this is PureScript, so I should use camel case. Okay, so 35 as an expression. We could now write our own little evaluator which takes expressions to ints, but I think that's kind of boring. Let's just compile it right away. So when we compile an expression, at least our expressions, what we want to get back is a WebAssembly expression. Okay, so compiling an expression takes an expression in our source language. So I'm writing down a pattern match for that now. So one of these, and it produces a WebAssembly. It produces a WebAssembly expression, which is actually just the array of instructions up here, right? And we're going to just leave the surrounding bits intact for now because we don't need more of WebAssembly's features just yet. All we need is to compile a single expression, and we can use the bit of boilerplate we've put around here. And all we're going to say in here instead is that we are going to have this function not just have a hard-coded sequence of instructions, but instead we're going to say compile expr 35. Okay, so that's what we're going to go for here. So if we have a literal x. What does that compile to? Well, really that's simple. That's just I32 const that value, right? If we have an addition, how do we add together expressions x and y? What do we need to do? Let's think about this. I'm just gonna fill out the shape here just so the whole thing compiles and we can think about what the individual holds here mean. Okay, so so we need to fill in this whole add. And what do we have? So this is supposed to be an array of instructions at the end. And we have in scope x and y, which are both expressions themselves. So what can we do? Well, we can say these are the instructions that compute the value of x in WebAssembly, right? So we can say, well, if I compile the expression x, I get the instructions that produce an x. And if I compile the expression y, I get the instructions that produce a y. So now now these are the instructions. And what do we need to do in WebAssembly, really, if we think about this? Well, we need to put these two values on the stack. So we're just going to say, well, first execute the instructions that produce x and put it on the stack. Then produce the instruction to call the instructions that produce y and put it on the stack. And so now x and y ought to be on the stack. And all we need to do now is say, well, and now I'm going to call I32 add, right? And it's very similar here, except that we're going to call multiply, right? And well, if we're being honest, we can just inline this. This is maybe a little easier to see. I just want to first show that we needed to do this transformation. Okay. And so now, if we go ahead and we run our compiler, we can already look at the output and see that this is exactly what we wanted to see. 3, 4, add them up, put 5 on the stack, multiply. And just to be sure, we're going to call our main function here, and it returns the value 35. That's cool. Let's try one more expression, maybe a little bit, something a little more complicated. So 35 here is just 3 plus 4 times 5. What if we said 35 squared? So this ought to be a little more complicated, which is also an expression. So what are we doing here? Well, we're saying, give me a multiplication of 35 and 35. And let's see if we can calculate this first. I don't know how to calculate it works. Damn it. I know Emacs has one, but so can I just say calculator done? Ah, that didn't work. So what's 35 squared then? Let's just check. So it's 1,225. Okay. Well, let's see if that is what we get when we compile and run this. Hey Vlad, how's it going? Oh, we're not compiling this yet. So saying this module is supposed to compile at 35 squared now. We are, I don't know when you joined, I'm assuming you joined just now. What we're doing here is we've come to the part where we actually started compiling expressions to WebAssembly. So we're no longer hard coding them. And right now we're trying to compute the result of multiplying 35 by itself. all's good. Baby's falling asleep, so I'm relaxing until I stream later. Yeah, that sounds great. You deserve some relaxation. So let's hope this works. 1,225. So that's 35 squared. So all of this works. And we're using WebAssembly's stack machine to produce this. Now that Vlad just joined, I don't know how familiar you are with WebAssembly. I'm assuming you're probably not at all. So how about I don't know, maybe you're familiar with stack machines though, but not at all. All right, cool. So let's look just for a quick refresher, and maybe others that joined might find this helpful as well. This is a WebAssembly program, and a WebAssembly program like this, when it executes, has access to a stack of values and a list of instructions, or a sequence of instructions that it executes. And we're executing these downwards, and our stack grows downwards because that's easier to write. So these instructions, when it sees, so the i32.const instruction just puts a constant onto the stack. So when we're starting to execute this instruction, the stack now has a value on it. And this is the same. It pushes the value 4 onto the stack and just moves on to down here. And then what add does is it takes 2 values off of the stack, puts them into CPU registers, if we're being very clear about what happens, calls add and the value, and puts the returned value back onto the stack. So after add is done executing, and we're, well, down here essentially, we have a state like this. So now whatever instruction comes next operates with a stack that has the single value 7 on it. Okay. And so now we're looking at a more complicated instruction. So that's how you just add 2 numbers. But if you have a more complicated instruction like this one with results in between, well, that works exactly as we did before. So here we get it. The stack is now 3. We execute this instruction. The stack is now 3, 4. We add. Now we have a stack of 7. And we are looking at this instruction. So this instruction puts a 5 onto the stack. And then multiply does the same as add, just that it multiplies the value. So it takes 2 values off of the stack, the uppermost, and it multiplies them together. Okay. And so that's how the WebAssembly stack machine works, and how we need to think about computation when we are compiling to WebAssembly. And it's a bit weird to look at this as a human, but it turns out for a compiler, this is almost the ideal way of representing instructions, because it's so easy to compile to, right? Because when we look at how to compile these expressions, what we can do is we can say, what we're going to do is we're going to compile every single one of these instructions, these expressions, into an sexpr, which is just an array of instructions. So we're just going to produce the array of instructions that ends up putting the value that this expression is supposed to produce onto the stack, right? And then when we're compiling an expression addition, we just we execute all the instructions that put x onto the stack, we execute all the instructions that put y onto the stack, and then we add them up. And the same goes for multiplication. So that's why this is so nice, because we don't need to think about nesting, right? It's just a linear kind of expression. And the stack machine, through its depth, basically handles the nesting for us. I don't think there's a stepper for this, because otherwise I'd show you how it steps through the, well, there is actually. Should we try something? No, let's not. At some point, we're going to look at Chrome tools or the WebAssembly, the Firefox tools maybe, and then we can step debug through our WebAssembly code. But I haven't set that up right now, and we need to put together a bit of JavaScript to make that work, and I'd rather not do that right now. unless I can make the Node Chrome debugging work, because then we don't need to set up anything. What do we need to do? Node dash inspect. Is that all? Let's try it. Let's try it. So when we say npx spago run, really what that does is it calls what I believe. Do we have an index.js file in here? I don't think we do. Nope. Let's just create one real quick. So what this is going to do is it's going to require our outputted main file, and it's going to call the main function on it. And so we can say node index.js, and this is going to say that it can't find this one. Oh, I think we need to do this. There we go. And so this works. And so now we should be able to say node dash inspect, like so. And it says debugger listening on, but it seems like the code has already run. But maybe we can restart it or something. So how does this work again? Inspect break. Okay, there we go. Dash brk, like so. And then we open about inspect in Chrome. Okay, so we say Chrome, and I'm gonna say about inspect. Open dedicated dev tools for Node. Do we have a connection? Okay, so we're stopped right here. So this looks fine, which is great. So let's step into the next function call, which takes us to main. And where I want us to stop is when right where we, oh, this is, so yeah, I want to step into the next function call, which is main. So here we go. So where do I want us to stop? I want us to stop at here. And then I want to step into that function call. Here we go. Well, we're not calling the function here really, are we? So maybe I don't think we can we can just do this, but we'll see. So if I do inst.exports, and then the function we're exporting is called main. Let's see if we can put a breakpoint here. Probably not. Okay, so let's just go and do that. So rather than just creating them, let's actually say we're going to execute the main function here. Okay, I'm gonna say let result, and then we're also going to log out that result. Okay, so let's kill this. I don't know if that's the right call, but we'll see. And I'll do this again. Chrome. Open dedicated dev tools for Node. Connection. We should. Do we have a connection? There we go. Okay, so the connection is here. We're ready. So let's step into main, I guess. So we're going to step over the require. We're going to step into. Did things already happen? No, they didn't. Okay, so where are we here? Oh, okay, I don't want to get out of there. Get out of there. Get out of there. We don't want the node loading code. Okay, so can we get the files here that are relevant? So, okay, so that looks more reasonable. We want to stop in main foreign.js. Wait, oh, we didn't recompile. I'm an idiot. So npx spargo build. Okay, and let's do that again. So I'm assuming it's connecting right now. Here we go. And so now I want to go into the main file. Is there like a file finder here maybe somewhere? File system, no. Node, file. Can I search in here? Control P. Oh, that looks better. So what's it called again? main/foreign.js. Okay, so foreign. Okay, it doesn't find it. Oh, I think we need to step over this thing. I want to stop in main. Can I tell it to stop in here? Continue to here. Okay, so apparently we made it all the way in here, and my cat is walking over my desk. Okay, so now it has found all of these things. So now inside the main foreign.js, this is where I wanted to stop. And that's my cat. So can we tell it to step one more? Can we go in here? I want to set a breakpoint inside instaexplorer's main, which is this WebAssembly. Here we go. That looks great. Okay, so we have a WebAssembly stack. Let's go. Can we? Okay, so here's the stack. Amazing. So we made it. My cat really wants outside, but he's not allowed to because he has actually hurt his paw. And so we were at the vet yesterday, and he needs to stay inside for a couple days, but he's not happy at all. Do we do a cat cam here? Just check. Say hello, Nemo. All right. Yeah, he's really not happy. Okay, so we've made it all the way in here. So this is the instructions we generated. Remember, this is 3 + 4 times 5. And then we leave the result on the stack. We add 3 + 4 again, and we times 5 the thing, and then we times 5 the result. So this is 35 squared, and that's a lot of cool cat gifs, cat emojis. I'm a fan. Okay, so let's see if we can step this thing. So if I step this, you can see that as we execute i32const3, it has now put the 3 onto the stack. Can I make this a little bigger? Yes, I can. Oh, no, that's too big. Okay, so how about this? And so the stack is now 3. As we execute the next, the stack is now 3, 4. We add, the stack is now 7. So it's doing exactly the thing I said it was doing. Now it puts 5 onto the stack. It multiplies them together. And now it just leaves that 35 on the stack for the squared multiplier we need later. It now it puts 3 onto the stack, it puts 4 onto the stack, it adds them up, puts 5 onto the stack, multiplies the two values, and now we have 2 35s left on the stack, and then it just multiplies together those two to give us 1225, which is what this function call ends up returning. So very cool that we can use Chrome's debugging tools like that to show something like that. I'll definitely use that again in the future when we build a couple of more complicated things. So that's one of the main motivations really for compiling to WebAssembly, is that you can use all of the amazing dev tools that we already have in the browser to try and debug the things you end up compiling. All right, very cool. So now that we compiled these very simple expressions, how about we get a little trickier? we could think, like, there's two things I could think of right now. I could allow let statements in here, which would make it so that we could bind individual expressions to names and then reuse them later on. Or we could say add the concepts of functions so that we could have procedures that we could call. So rather than having a single expression, we could add the ability to define functions here. And now the question becomes, which of these is it going to be? Actually, functions might be more complicated. So let's try to compile expressions that allow binding things to variables first. So I'm going to call these complex expressions. So a complex expression is has a bunch of bindings which bind expressions to names, right? So this is an array of name. So bind let's call it a name. So this is the name something is being bound to, and this is the expression that's being bound to that name. And then we also have the final expression. So this is where we then get to use all of these names. This is a type. What does it not like? These need to be double colons. Programming in languages that use different syntax is too much. Okay, and then we need, in our expression language, we now need the ability to reference these names. So maybe I'm going to call these expert2s because they're a tiny bit more complicated than the expressions we've compiled so far. So this is an expert2, and all these expert2s get is the additional ability to reference a name, and that's a string. And oh no, doesn't like that we've declared these to allow, well, constructor names exist in just in the global namespace. So we I'm just gonna get rid of this. We're gonna compile a new bunch of expressions now. That's what we're gonna do. And we're actually going to compile a C expression here now, which is going to be a bit more tricky, and we'll get to that in a bit. I'll just comment it out for now, and I'll talk about why it's a little more tricky now. So let's just call these experts like so. And now it says, well, if you give a name, this is the name, can we just compile an expert like so now? Well, not really. So in order to compile a expression to a WebAssembly expression now, what we need is an environment here. And this environment is a mapping. I don't know if I have maps yet. We'll see. Is a mapping, no we don't, from names to indexes, and that's a local index. So what does this mean? In WebAssembly, we have the concept of locals, which are variables that are local to your function. So if we check out the if we check out how a function is defined in here, functions, we'll see that it has access to locals. And locals declare a vector of mutable local variables and their types. these variables are referenced through local indices in the function's body. The index of the first local is the smallest index not referencing a parameter. So far, we do not reference parameters at all because we do not have arguments to functions. We don't define our own functions yet. So what this is going to be, these are locals refer to this array of bindings, and the local number 0 is going to refer to the first bindings we've made here. So let's write the expression we had before, so 35 squared, by binding an expression called 35. So let's call it 35 squared again. And this is a complex expression. And 35 squared has a single binding. It binds the name 35, right? And in order to produce 35, you need to execute the following expression, and we've written this down a few times now, so I'm just going to type it out one more time because I forgot to save it, unfortunately. So we're going to add together 3 and 4, and then we're going to multiply the results by 5. Right. Like so. Just a bit of formatting. Here we go. And so, okay, so we're binding the name 35, and we're assigning it an expression that computes 35, essentially. So what we need now is the body, and the body now is actually going to be a multiplication of the name 35 and the name 35. Right, so we're referencing the variables we defined before, and maybe name is a bit of a terrible thing to call that, if we're being honest. So let's just call it var, right? And so now in here, really, what we could do is we could say the env maybe for now is just an array of names, and the index in that array represents the local index. So let's try that first. So what does the expression name var of name compile to? And what we need to do is we need to say find index. Maybe there's an index of function. We'll figure it out. No, find index or something. Nope. I'm just gonna say find for now, so we can import array. So what do we have? Do we have an index function? Just index? No, that just. So what kind of finds do we have? There we go. Find index. That seems good to me. And we need to find an index that says, well, the value here is equal to v, and we need to find that inside the env, like so. Now this gives us back maybe an int. So what do we need to do? Well, we need to call the function local, so that we need to add the instruction local get in here. But now the whole thing returns a maybe. And what I'm going to do for now is I'm just going to say we're just going to unsafe partial from just here because, well, we are not going to deal with missing names here. That's going to be the job of the type checker at some point. Okay. And so now what we need to do everywhere is pass through the environment when we say compile expert. Like so. Okay. So now, when we want to compile complex expressions, things get a little spicier, because compiling a complex expression no longer returns an expression in the Wasm world. Instead, it now needs to return a func. And that is because it needs to declare a bunch of locals. But maybe for now we could just say that compiling a complex expression, like so, returns you a set of instructions that this complex expression corresponds to. So I'm just going to call this body again, and this is actually an expr, but it also needs a bunch of locals, right? And here really what I'm going to do is I'm just going to say that locals is, because we're just dealing with ints for now, I'm just going to say, okay, how many locals do you need? And that's just going to be that for now, I think. We'll see if it works out. I'm hoping it does. So if we compile a complex expression, what does it correspond to? Well, bindings and the body. So that's what we get to work with. We want to compile expression on the body, but we need to fill in the env here. And the env we get from while computing the bindings, really. We're going to say computed bindings here, or like maybe let's just say, well, let's figure this out. What we need to actually we need to produce here? We need to produce an environment. Okay, so the environment is just an array of strings. So what we can do is we can just say, well, we're going to map the _name function over the bindings, which is going to give us exactly that env that we need. And the whole thing here just produces the body then. And the number of locals we need, that's the length of the bindings. Okay. And all that seems fine. The problem is we're never generating the expressions that are supposed to initialize these bindings. Okay. And so how do we do that? That's the more interesting thing, really. Right. So we need to compile these expressions, but they also need an environment. We could say, as a simplification for now, so we could say initialization here is just the following. We're going to call folder map over the bindings. I'm going to flip this one actually. So now we can write down the function here. So what is a binding? Well, a binding, as we said before, is a name and an expr. The name we don't need, we just need the expr. But we need the index. So folder map with index, I believe is what it's called. So how does that look? You get the index first. So this is the index and the expression. So what we're going to do is we're going to say, okay, so I'm going to compile the expr. I'm going to say the bindings do not get to use previous bindings for now. And I'm just going to compile this thing with an empty environment, and this should give us an array of instructions, right? And then we're going to also store the value that this expression produces, so that's local set, into the local that corresponds to this binding. So that's the index here. And then before we do anything, we're going to initialize our bindings before we compile the expression, or like before we execute the instructions that our expression produces. And so what I hope is now that we can say up here, well, this produces a body and a number of locals. Let's be a little, so let's say compile function here, which is not really what this is. So I'm just going to say temp function. It takes a complex expression and it produces a WebAssembly function, right? And so what we're going to do first is we're going to say, well, we're going to compile this expression. So compile cexp, and that gives us a body and the number of locals we need. That's just an int. And then we're going to say we're going to produce a WebAssembly function, and the type is still going to be 0. We're going to hard code that for now. The locals are going to be, and the locals up here are just a number, or an int, but we need to specify the types here because we only have ints for now. We can just use replicate here. We can say we're going to replicate locals times the type i32. Okay, and then the body, that's actually just the instructions that we produced up here so far. And what I'm going to do is I'm going to say, okay, so now this funcs thing over here is going to be temp function of 35 squared, because that's the expression we've built so far. So that compiled. Just a second. All right, all's good. So that produces now a function. And let's try to run our compiler. So npx spago run, which is going to produce the bytes.wasm file, and then it's going to feed the output into the WebAssembly interpreter of Node. And as we can see, this actually produces the result we want. But what we're also going to do now is we're going to look at the generated WebAssembly here. So this is the WebAssembly. As we can see, we are exporting the function main here because I renamed this one to say main. The type, all of that is the same, but this is the expression we're working with now. Okay. So this is our initialization block. This is where we declare that we have a single binding, which is the variable we've called 35. And then we're producing the value 35. So this is the expression that produces 35. And we're setting the local 0 to hold that value. Okay. And then our expression just gets the variable 0 twice, multiplies it, and that's how we square 35. Now we could say, let's be a little trickier here maybe and say let's produce a different value. Let's say we also bind the value 2. So let's say this is 2. And well, 2 is just the literal 2. And we can multiply 35 by 2. Right? Let's see what this produces. So first, it produced the value 70, which is great because that's the value we wanted to see. But now look at what it generated here. So it's saying we have locals from 0 to 1. So now we have 2 locals of type i32. And the first one we initialized by setting it to 35, as we did before. Then we push the value 2 onto the stack, and we initialize the second variable with that. And then we get 0 and 1 and multiply the 2. Okay, so this now lets us essentially write expressions like so, if we were to ever write a parser for this thing. So we can say let 35 equals 3 plus 4 times 5. Then we can say let 2 equals 2. And then the expression where we're doing these things is 35 times 2. Like so. And let's just do this for syntactic reasons. And so you can see how this now starts to actually become a compiler, because this looks more like a program than before. So we have variables now, right? We can define variables to hold certain values, and then when we compile this, we compile it using WebAssembly's locals for functions. And I think actually this is kind of a good point to stop. We've been going for a while now. We have a compiler that can compile simple expressions, and it can actually compute, also bind a couple of variables and use those inside our simple expressions. We're compiling all of that to Wasm. And the next time around, I think I want to start looking into generating multiple WebAssembly functions, because right now we're just generating a single one. We might also want to think about scoping. So how wouldn't it be cool if we could say bind the variable 7 up here, right? Say that that's that, and then use 7 down here, right? And so we have this like scoping where certain variables are available to compute others. So we're not doing that yet, but we could look into that next time around. And it's, yeah, I want to start being able to write functions. And actually, because Wasm is pretty cool, we can actually do recursive functions very easily. So it's very possible that the next time around we'll be able to define Fibonacci in our language, which would be kind of cool. So thanks everyone for watching. Thanks for the cat pictures. Hope you're doing well, and see you the next time around, I guess. Bye-bye.